Good morning, dear students. Today we'll discuss about the next part of capacitor. We have already done capacitor part 1. So today we'll go for capacitor 2.2. Little more developed version. What is it? Okay. So till previous class we have learned capacitance of parallel plate capacitor, that is C equals to epsilon naught A by D. This is the last part we have derived. Okay. Today we'll learn that if we need a desired capacitance in a circuit, then how can we able to generate it? Maybe the capacitor we are having there, the desired capacitance I am not getting. So then how can we able to find the capacitance whatever I want in a circuit? And for that case we need to combine the capacitors. So the next thing we will do, that is combination of capacitors. Remember, to find the desired resistance we have combined the resistances. Okay, the resistors we have just combined it to find the desired resistance in a circuit. So similar thing we have done here also. To find the desired capacitance we have combined the capacitors, and mainly the parallel plate capacitors. Okay. So how many types of combinations are there? Definitely just like just like resistors, there are series and parallel combination. So it is not needed for anyone to show you what is a series combination, what is a parallel combination. No need to define it because you have learned it in resistors. So series combination means, assume we are having three capacitors of capacitance C1, C2 and C3. If we connect it one after another, end to end contact, that should be a series combination, just like this. Assume it is C1, C2, C3. We all know we denote capacitor, okay, by some parallel lines, by two parallel lines. Okay, here I have connect one source. So this is C1, C2, C3, and here the potential I have taken, that is V. Now from here what we have to find out? See, for the case of resistance we are finding out the resultant resistance, and here also we have to find the resultant capacitance. Why we have to find the resultant capacitance? Because it is our need that if I connect three capacitors in a series, then what will be the resultant capacitance, and by that idea we can use it, okay, in other cases for combination of series. Okay, so let's start. Whenever I have connect a source here, definitely as this terminal is connected with positive terminal, so here plus Q charge will induce in this plate. Okay, and due to the plus charge, there will be a charge induction in the another plate, and that should be equal, that is minus Q, that is Q minus. Okay. Similarly, if I am talking about here the negative charges will come. Okay, So here minus, Q minus, and here it will be Q plus. Okay, and here you can say that as they are also same Q plus and here Q minus, charge will generate. Q plus and Q minus, charge will generate. From here we can say that the total charge in series is constant. Just remember, whenever we are thinking about the resistance, there the total current in a circuit through all the resistances which are connected in series, they are constant. And here instead of current, what we are taking? We are taking the charge. Okay, basically the difference is not there, it is same. And we all know that the rate of flow of charges, this is the rate of flow of charges, that is known as current. Okay, so in a series combination, the total charge is constant. So if the total charge is constant, so the potential shouldn't be constant. So potential across, V is the potential across each resistance, each capacitance will be C1. So we all know that Q equals to, you all know that now, C equals to Q by V, or V equals to Q by C, that we have learned earlier. Okay, so here if I am talking about the potential here, so the potential V1 across C1, if I see, that should be Q by C1. Across C2, it is Q by C2. Across C3, it is Q by C3. So across each resistance, here it is V1, here it is V2, and here it is V3, exactly like resistances. In resistances, you remember the total potential is not constant across. If I'm talking about in a series combination, across series combination, we have learned that it is not constant. Okay, and here also the same thing we have seen, that across series constant the potential difference is not constant. So we can mention here one thing, that total potential V equals to V1 plus V2 plus V3. Total potential should be the sum of three potential, V1, V2 and V3, right? And then instead of V1 we can write Q by C1 plus Q by C2 plus Q by C3. That thing we have taken. Now instead of three capacitance, why I'm telling resistance I don't know. Okay, because of continuously telling by resistance all the time, and we are very much familiar with that, and that's why I'm telling resistance, but it is capacitance. Instead of three capacitors, if we take a we take one capacitor of capacitance CS. CS, as we are talking about series, that's why it is CS. So from here we can write V equals to Q by CS. We can say if it is equation 1 and it is equation 2, we can make these two equal. So we can write from 1 and 2. Okay, so the place is not much here, we have to write here, it is better. So from 1 and 2, Q by CS is equals to Q by C1 plus Q by C2 plus Q by C3. See, Q will be cancelled out and the answer will come 1 by CS is equals to 1 by C1 plus 1 by C2 plus 1 by C3. So if the capacitors are connected in a series combination, then the sum of the resultant capacitance will be, the reciprocal of the resultant capacitance will be the sum of reciprocals of the capacitance we have used. Okay, exactly like the parallel combination we have seen in resistance, and that is occurred in series combination in capacitance. Okay, so simple thing, if I'm talking about an example, assume three capacitors, assume it is one, it is two, and it is three. Okay, 1 microfarad, 2 microfarad, 3 microfarad. Now you may think, sir, why it is microfarad? We know the unit of capacitor is farad, but farad is a very large unit. Okay, generally we use the unit that is microfarad, mu f. So if it is connected in series, then the resultant will be 1 by C equals to 1 by 1 plus 1 by 2 plus 1 by 3. So 6 plus 3 plus 2. Okay, 11 by 6 and C equals to 6 by 11 microfarad. So this type of numericals what we have done in the case of resistance, so same kind of numericals can come for capacitance. Okay, exactly same. The combination of resistances you have learned there, the network has come in with different resistances. Here also the same kind of thing can come. Okay, I think it is clear. Now we'll go for parallel combination. Series combination is done. We'll go for parallel combination and then we'll see little bit of numericals also. Parallel combination. I think it is not difficult for you because as you have learned once the resistance, so for capacitance it is same, but it is different, exactly opposite to the resistance. For resistance whatever you have done, for capacitance it will be exactly opposite to it. So we are coming to parallel combination. So parallel combination, you know that the connection will be just like this. Instead of resistance we have given the capacitors. Instead of resistors we have given capacitors. Here also I am taking same capacitance of C1, C2, C3. Potential is V, but here it is connected in series. I'm sorry, in parallel. Here it is connected in parallel. So it is clear that the potential across each capacitance will be same. Potential across each capacitance will be same. So across C1 also the potential will be V. Across C2 also it is V. Across C3 also it is V. Okay. So as the potential is constant but capacitance is different, we know the equation Q equals to CV, total charge equals to capacitance into potential. Now as the potential is same but capacitance are different, so charges induced across the capacitors, that will be changed. Charges induced across the capacitors, that will be changed. So let here the charge will be Q1, here the charge will be Q2, here the charge will be Q3. So Q1 is equals to C1V, Q2 is equals to C2 into V, and Q3 is equals to C3 into V. Three charges, three expressions. So if I'm talking about the total charge, so total charge Q is equals to Q1 plus Q2 plus Q3, because your charge should be same. So instead of Q1 you can write C1V plus C2V plus C3V. So common V, C1 plus C2 plus C3. Okay. Now instead of taking three capacitors, if we take one capacitors of capacitance CV. Okay. So instead of three capacitors, one capacitor of capacitance CP is taken. Okay, so what capacitance we have taken? Its capacitance is Cp. So from here we can write Q equals to Cp into V, as per Q equals to Cv. So we can write Q equals to Cp into V. Instead of this 3 we have taken only one. Okay, that is Cp. Okay, if I am talking about the diagram, it is just like that. Here it is V, here it is Cp, and here total charge is Q. Clear? These two equations are same. Both are representing the charge. So equating 1 and 2. If I equate 1 and 2, we will get Cp into V is equals to C1 plus C2 plus C3 into V, and Cp equals to C1 plus C2 plus C3. Exactly same with the combination of resistances when it is connected in series. So here you see it is just change. Okay, for resistance, what is there, what equation we have seen in series, that is coming into the parallel, and what is there for case of parallel, that will go on to the series of capacitors. Exactly this change is occurred, other things are same, no other changes is occurred. What type of numericals can come from this type of questions? Very easy. Assume what numericals you have done simply for the case of resistances. Just like I'm just doing the arbitrary numerical, maybe it is coming in fraction. Okay, so assume okay, so it is 2 microfarad, it is 1 microfarad, it is also 2 microfarad and 1 microfarad. I told you to find the resultant capacitance of this uh, network AB, this combination. So it is clear. We can redraw it by this way. See, from A there are two terminals. One you have to go this way, another one you have to take. So one, if it is taking A, it is B, it is C, and it is D. So it is A, then it is B, then it is C, and then last one is D. So if I modify the diagram looks like this. So this three is connected one after another, end-to-end contact. Now put the value. It is 1, it is 2, and it is 1 again. And here it is 2. Okay. So how can we be able to do that? So ABC is connected in series, right? Just write it. So for series, 1 by CS is equals to 1 by 1 plus 1 by 2 plus 1 by 1. So here it is 2, 2, 1, 2. So 5 by 2. Right? So 5 by 2, that is CS equals to 2 by 5. 2 by 5 microfarad. Okay. So your diagram will be modified. Instead of taking 3 capacitance at the top, that is coming only 1. It is 2 by 5 microfarad, and at down it is 2 microfarad. Now, so parallel will be, it is connected in parallel. So CP equals to C1 plus C2, that is 2 by 5 plus 2, 12 by 5 microfarad. So if you do it, 5 to the 10, 4, 2.4 microfarad. Okay, that will be your answer. So this type of numericals may come. Okay, it may come more harder also. So today we will not go further about more hard numericals. For that I will make another video. There we have to discuss only the numericals of capacitor. Okay, so here I am just showing that what type of numericals may come. Okay, this type of combination, what we have done for resistances, this type of combinations will come for capacitance also. Okay, now we have to learn one very important thing, that is energy stored in a capacitor. Energy stored in a capacitor. That when we are talking about a capacitor, how much energy is stored by it? We have seen what is capacitor, that two opposite charges are just kept at a very close distance. It can be kept by two parallel plate, but it can be by another way also. So next is very important, energy stored in capacitors. See how I have done it, and just see what logics I have used. Okay, because without logic you cannot able to do this type of questions. And don't try to remember it, don't try to memorize it. If you want to memorize, then it will be difficult for you and me also to make you understand. Assume it is two plate of a capacitor. Here it is positive charge plus Q, here it is negative charge minus Q. Clear? Now we all know that there will be an electric field is acting from plus to minus, right? So the electric field, the direction of electric field is this. This is the direction of electric field. It is acting and it just try to oppose it. If we think that how these two charges are coming to the plate, then you might be telling that, sir, we have just connect a cell here with the positive terminal, it is connected, that's why here positive charges, here it is connected with negative charge, that's why it is connected with the negative terminals. But we can say it, we can explain it by some another way also. What is that another way? Let's see. See, assume initially these two plates are neutral, there is no charges. Assume one by one I have taken one charge and give it here. I think it is difficult for you. Try to understand. Two plates which is completely neutral. No charges is there. Now I have taken one charge small q. I have taken it from this plate. Okay. And put it here. So as it is added, as initially it is neutral, one small q is added, so it is plus q, and one small q is taken here, so it is minus q. Similarly, another charge, assume it is q dash, it is taken from here and put it here. So here the total charge is now plus q dash, and as q dash is taken from this plate, okay, so it is minus of q dash. So like this way we can assume that, okay, we can assume that like this way one by one charge is decreased in the previous plate, okay, in the second plate, and one by one charge it is increased here. Now here also one problem is there. What is the problem? See, whenever in this plate there is no charge, so it is not a problem to take a charge q and put it here, because as there is no charge, there is no potential. So as there is no potential, so no opposing force is acting here. As there is no potential, try to understand it. As there is no potential, so no opposing force. Here this charge will not oppose it, and this charge will come here one by one. But once plus q charge has come, then when another minus q have taken, then it will feel a force, because previously already plus q charge is here, so it just try to oppose the another charge, it just try to prevent the coming of another charge, okay. But this charge, that is minus q, is just go and put it here, and more charge is coming to this plate, more potential is there, and more repulsion. If any another charge is want to come in here, then it should have to do much amount of work, understand? Okay, so this is the phenomena we have shown you, that by which method the plates are getting charges, the plates are getting charges. Okay, now you may ask that, sir, is it the procedure the charges has come? Practically no, but theoretically if we understand it, then it is easier for you to calculate the energy stored in capacitor. Again, I'm telling you the thing, try to understand, because based on that everything will be calculated. What I'm telling, initially there is no charge, I have taken one charge q and put it here. So here the charge is now plus q, here the charge is minus q, as I have taken q from here. So once the charge is coming here, it will give there will be a potential created in this plate. So potential means if you want to take another charge q dash, you have to do work. Okay. Again, if q dash is coming and here it is minus q dash, So here the potential will increase more, because you know, more the charge, more the potential. So one by one charge is coming, the potential is increased. More potential is increased, it is difficult to take another charge from the negative plate to put it in positive plate. That is our target. Now coming here, so this is the preliminary concept we have to take. Now coming to here, this is a capacitor. Assume here its capacitance is equals to C. Okay, and charge stored is equals to Q plus Q minus Q. So charge stored is Q. So potential V equals to Q by C. We all know that potential V equals to Q by C. Okay, now see here, if a small charge dq is taken from negative plate and put it to positive plate, work done will be dw. Why I am writing this one? This is the concept, this is the situation is now. Now I am taking what? Now I am taking one charge dq from the negative plate and putting it to here at the positive plate. So if you want to do it, you have to do work against its potential, because we have already told that potential V equals to Q by C. So how much work you have to do? The dW. So dW equals to how much? dW is equals to V into dq, because we know work done W equals to V into Q. Here I am taking small charge dq. Okay, this Q will be capital, then it will be easier for us. Okay, so V into dq. As I am taking dq charge, so that's why the work done is V into dq. Okay, I think there shouldn't be any problem. Now, if I want to find out the total work done to form the system, total work done to form the system. Okay, so it should be integration of V dq. Okay, integration of V dq. Okay, initially you see, initially there is no charge, so initial limit is 0, because initially whenever we have taken the two plates there is no charge, and finally the charge gone to capital Q. So 0 to Q, V dq. What is the value of V here? Now V equals to Q by C. So integration of Q by C dq 0 to Q. 1 by C, it is a constant, it is coming out. Q into dq, it is Q square by 2. Q square by 2. And the limit will be 0 to Q. Upper limit minus lower limit, 1 by 2C, Q square minus 0. That means Q square by 2C. So that much work you have to do to form the system, or to form the capacitors we have seen with the charge, that is Q square by 2C. So how much work you have done, that much work should be stored on the capacitor as its energy. How much work you have done, that much work should be stored as its energy. So energy equals to, energy is equals to Q square by 2C. Q square by 2C. Again, we know that one interesting thing you see. We know Q equals to CV, that we know now. So if I put the value here, energy equals to half of Q square means C square V square by C, or half C V square. Another form of energy. One is Q square by 2C, another one is half CV square. Again, we all know that Q equals to CV. Q equals to CV. So by this equation, we can write half CV into V. CV square, CV into V. That is half of Q into V. Half of Q into V. This three thing, number one, number two, and number three. This three is the equation of energy. This three is the equation of energy stored in capacitor. As per the informations are given to us, depending on that we can able to find the energy. As per the information is given to us, we can able to find the energy. Okay, I think it is clear enough. Assume what type of question can come, the derivation of this equation it may come. Okay, apart from derivation also, the numericals are come like this. Assume if it is told that a capacitor of capacitance uh, 8 microfarad is connected with 100 volt of potential. Find energy. How you have to find it? So what the things are given to you? Capacitance is given to you. Okay, that is C. So C equals to 8 microfarad. Micro means 8 into 10 to the power minus 6 farad. Okay. V is 100 volt. So energy, one equation of energy is half CV square. So depending on the thing, what the things are given to us, we have to find the equation half CV square. So half into 8 into 10 to the power minus 6 into V square means 100 into 100. 4. It is 10 to the power 4. So 4 into 10 to the power minus 6 into 10 to the power plus 4. So 4 into 10 to the power minus 2. Okay, that much of joule of energy is stored here. So this type of numericals can come, okay, for the energy calculation of capacitor. Now, if I am talking about energy stored in a capacitors, if they are connected in series and if they are connected in parallel. Energy stored in capacitors if they are connected in series and if they are connected in parallel. Let's see. Okay, I'm erasing this thing. If you want to see it, pause the video and see it. So for that reason, I am going backside to make your vision clear, to see the board so that you can able to copy it. Where you want to copy, pause the video, copy it and then play it again. Okay. Energy stored in capacitors connected in series parallel. Okay, so no need to draw the diagram. We know that what is the series combination, what is the parallel combination. So series combination means we all know the combination 1 by Cs equals to 1 by C1 plus 1 by C2 plus 1 by C3 plus data. How many capacitors we can able to take. So here, whenever we have to find the equation, we have to follow such equation where C is coming in denominator. C is coming in denominator. So if I want to find the combination of energy in this capacitor, so I am taking the equation Q square by 2C, and for this case it is Q square by 2CS. See, C is in denominator, or we can write Q square by 2 instead of CS, 1 by C1 plus 1 by C2 plus 1 by C3 plus dot dot dot, wherever you can take. Okay, because we cannot able to take that equation where C is in numerator. If you take it, then it should be wrong. If I am coming to the parallel, here we have taken Cp equals to C1 plus C2 plus C3 plus up to infinity. How many capacitors you can able to take? So here, if I want to find the energy, E equals to half C V square. Definitely I will take that equation where C is in numerator. We have to take that equation where C is in numerator. Okay, so half of, instead of C I have to write Cp. It is C1 plus C2 plus C3 plus dot dot into V. That should be the energy. Okay, P square. That should be the energy stored in parallel plate capacitor. For series and for parallel plate capacitor, how much energy can be stored, that we can able to find out by this way. Okay, now going to the last part of today. So I think that I'll go more, but if I go more, then it will be hectic for you to understand. Okay, so I'll not go much. The last topic we'll discuss today, and then the next video will come later. Okay, so energy density of parallel plate capacitor in a given electric field. So energy stored in capacitor U equals to Q square by 2C. Why I am writing U? Because as here we have taken electric field, so here must be, we have to take electric field that is denoted by E, and energy E, electric field is also E, that may be combined. So that's why I have taken U here. So U equals to Q square by 2C, and capacitance for parallel plate capacitor is equals to C equals to epsilon naught A by D, where A is the area, D is the distance between two plates, and epsilon naught is the permittivity in free space. So I am not writing this thing. Now I am coming to the electric field. Okay. Electric field. We have calculated earlier also the electric field of parallel plate capacitor, but I am just doing it here because if I write directly, then it will be a difficult thing for you. Whenever we are finding out the electric field of an infinite long sheet, you see the derivation is given in electric field chapter. If you see it, that is electric field for an infinite sheet is equals to sigma by 2 epsilon naught. Okay, it is sigma by 2 epsilon naught. Okay. If I am talking here, I have add one more plate. Okay, I have added one more plate. So here the electric field will be increased. How much it will be increased? Let's see. When we are talking about two plates, here inside there is positive charge. If it is connected it to the positive terminal, and if it is connected to the negative terminal, here it is minus charge. So if I am talking about only the positive plate, here we have seen the electric field is acting in this direction, that is sigma by 2 epsilon naught. Sigma by 2 epsilon naught. And here for the another plate, you see another plate is there. So for another plate there will be an electric field, and the electric field you see for the minus charge, that will also direct in this direction, because positive will repel and minus will, the direction of the electric field lines is towards it. And here also, as it is a plate, here also it is sigma by 2 epsilon naught. So for positive plate, sigma by 2 epsilon naught. For negative plate, it is also sigma by 2 epsilon naught, but the direction is same. For positive plate, it will repel, and for negative, it will attract, right? So total electric field, that will be sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So it is sigma by epsilon naught. So you have to remember, for a parallel plate capacitor, the electric field will be sigma by epsilon naught. Sigma by epsilon naught. That things you have to remember. I'll just erase this thing, otherwise it is difficult for me to calculate. So I'll erase this. Those who have not written, pause the video and write it down. So electric field is equal to sigma by epsilon. We can write directly, that is equals to E. Sigma is what? Sigma is charge density for a surface. So it is sigma equals to Q by A. If the total charge is Q and area is A, so it is Q by A. So instead of sigma, we can write Q by A epsilon equals to E, or from here Q equals to epsilon naught AE. Why we have done so much of things? Because we want to find the total energy, and total energy I have taken Q square by 2C. So for Q we have to find out something now. So we have to put the value here. So this is equation number 1 and this is equation number 2, or you can take it is 3, it is 2 and it is 1. So putting the value of 2 and 3 into 1, so energy is equals to Q square, if you do, epsilon naught AE whole square by 2 into epsilon A by D. Okay, epsilon AE whole square by 2 into epsilon A into D. So it is clear, 1 epsilon A will be cancelled out. So at top it is epsilon naught A into E square by into D by 2. Epsilon naught A E square into D by 2, or you can write half of epsilon E square into A D. What is A into D? A into D, you see the volume occupied by the capacitor. If the area is A and the difference between them, it is D. So A into D is what? Volume occupied by the capacitor. AD equals to volume occupied by capacitor is equals to A into T. Here we are finding energy density. Energy density means energy per unit volume. So U equals to epsilon naught E squared AD. We can write U by AD is equals to half of epsilon E square, and that is small u, and that is energy density. So what is energy density? Energy density is nothing but energy per unit volume. Energy per unit volume. So this equation gives us the energy density of parallel plate capacitor. It is important for the board. Not only that, many question is coming in competitive exam from this equation. So apart from the derivation also, it is important to remember the equation half epsilon naught E square, where epsilon is permittivity in free space and E is the electric field for a parallel plate capacitor. Okay, thank you.